so one is acceleration. That's not news. One is almost the same exact question as 24. So no real big fuss there. Two is gravitational mass versus inertial mass. One of the two things that they tried to talk about, but didn't sound from conversation like people had picked up on that idea very well. But gravitational was a choice, inertial was a choice. 4 to 9, we have gravitational, electric, magnetic, nuclear, and weak interaction. Put the stars on gravitational, electric, and magnetic. If they mess up the stars, go like half a point per star. If they got extra ones, if they took them away, whichever way they mussed it up. 10's electric, 11's frictional and mechanical, 12 is nuclear and weak interaction both, 13's gravitational, 14's the Newton, it's a kilogram times a meter per second squared, 16 is distance, 17's the study of forces that cause motion, 18 study of motion, 19 Galileo, 20 an object resisting a change in motion. They need to have the change in that answer. 21 there's a lot of stuff. So an object at rest tends to stay at rest. If they don't say that, there's a half. Object in motion tends to stay in motion. If they don't say that, we lost a half and we're already maybe out. At constant velocity is a phrase in that part about the motion. So if they don't have that, they're out a half. If they try to put the word speed in instead of velocity, they'd still be out the half. Unless acted upon by a net outside force. So object at rest tends to stay at rest, object in motion tends to stay in motion at constant velocity, unless acted upon by a net outside force. Sometimes you'll hear that said, stay in motion in a straight line. That's the way some books will say that. At constant velocity has you covered, because if you're moving in a straight line and then you get off your straight line, you just changed your direction. And when you change direction, we have that covered if we use a word that's vectors, because vectors include direction. So by saying constant velocity, we have ourselves covered that we would have to be in a straight line. 22, rest is a choice, constant velocity is a choice. If you want synonym choices, rest means a zero velocity, constant velocity synonym is zero acceleration. 23 is F equals ma. 24, just like 1, was acceleration. 25 is that mass is the quantity of matter, and that's kilograms. The weight is Earth's gravitational force, which is Newton's. And then a fifth point in this question is to say that weight changes from planet to planet. So weight is the one that changes. That's a fifth point in there. 30, W equals mg. 31, we're multiplying 9.8, and then we're dividing in the second blank by 9.8. If it's only a 1-point question, those are half a piece. There were some things earlier like that also. 11 and 12 had 2 answers, but only for 1 point, so it'd be a half each. 32, it's got to have 196. If they forgot the newtons, I'll let that go for today, but it really should have the newtons on there, probably. But since I didn't put kilograms on mine, I understand if you didn't want to put newtons on yours. I just didn't want to put kilograms on mine, because then I give away an answer on an earlier question. 33, acceleration of 6 meters per second squared. If all they said is 6, but didn't say what that would be, I'll give them half a point for just having a 6. If they say acceleration of 6, now we're talking. Ideally, we'd say an acceleration of 6 meters per second squared, but I'm not going to hassle you today about the meters per second squared. I didn't do units, so I understand if you didn't do units, but the reason I'm not doing units is because there's questions that ask you what the units are, and I can't really give away the So if you take a peek at the practice test, you'll notice that the new vocabulary goes up the number.
53.
That's the quiz. So in terms of new notes on this 6, 6, and 7 reading that I just did, I have some stuff on the board to get you. And then just on my other paper, I wrote a couple things, so I'll just read you what I wrote and then we'll hit the board in a second. So on the 2 and 3 section about the 2 kinds of mass, I had gravitational mass and inertial mass. When scientists historically had been thinking about measuring gravitational mass, they always used a tool called what? Anybody pick that up?
Wait, say the question again?
The tool for measuring gravitational mass.
The base beam or the beam balance?
Beam balance is the answer. My closest thing I could do of a description to a beam balance for you that you have probably personal life experience with is like the doctor's scale. Like you go to the doctor and they have that scale with a beam that they're trying to balance, hence the name. So the doctor will usually like eye you up if they're still using these kind of scales. And there's a pretty big weight that they clunk to the nearest 50 usually first. So they'd sort of eye you up and be like, you're probably between 100 and 150. So they clunk it to the 100 mark. And then there's like a slide thing that they'll slide until eventually it balances. But if they guessed wrong and they guessed you were between 100 and 150 and you're actually 170, would this ever balance?
No.
No. They'd have to then re-clunk this over to 150, slide you till they got to the 170. If you were really 240, well, you're another clunk away. Okay, but there's a big weight that they'll clunk to the nearest 50 usually, and then there's like a slide thing, and eventually it balances out, like the medieval scales that actually like balance. It's the same concept. So when they're thinking gravitational masses, they're historically measuring with a thing called a beam balance. Inertial mass was a different sort of concept for measuring mass, where they would try to figure out the mass of things by just working this equation. So and under inertial, throw the note, F equals ma on a frictionless surface. If they could find a frictionless surface, they could try to figure out what the mass of an object was by putting a force on it, measuring its acceleration, and seeing how that goes. You probably wouldn't enjoy that at the doctor's. They put you on a frictionless surface and give you a shove and measure how fast you go and then figure out your mass from that. That's probably not your favorite thing that they would do to you. The beam balance seems like a little more effective way to do that in the doctor's office. Then an important famous historical scientist kicked in and settled up with an idea that those two amounts are always the same. Who was that guy?
Albert Einstein?
Einstein appeared for the first time in our book in this section. So gravitational mass was one way they were thinking about mass and measuring mass with the beam balance. Inertial mass was a different way they were sort of conceptualizing how to measure mass with F equals ma on a frictionless surface. Einstein comes up with, these are the same thing, do whatever you want guys, but you're going to get the same result by both of these mechanisms. So some of that I think makes the next quiz. I think Einstein makes an appearance on the next quiz somewhere on the review sheet. It's in there. The other thing that more impacts your homework tonight life is this. These aren't hard ideas, but this sometimes messes people up for a couple days. My theory is people got spoiled by the homeworks being really, really easy the last couple days. And then today adds in a layer of complication. It's not heavy complication, but it makes the problems harder and people sometimes takes a day to digest this. So there's two kinds of forces that we need to be sort of aware of. There's a thing called net forces and there's a thing called applied forces. And I dropped this word in earlier in the chapter because I knew this was coming, so today's the day that it matters. Are the net forces more or less? Less. We talked about this, the word net, in relation to something else another day, and Danielle expressed an opinion that day, if that sparks a memory. What were we talking about the net? About some other context entirely? Paychecks. Your net is actually what you get paid, but that's always less than what you're sort of advertised. Why? Taxes and other things. Okay. Net forces are always less than applied forces Same concept as your paycheck in a sense. Taxes waste some of your paycheck away. There are other things that waste away some of our forces. If I'm acting in a horizontal direction trying to push things, what wastes some of my effort? Friction is correct. Anytime we have things moving horizontally, friction gets involved and hurts us. Okay, so if I have a human capability of pushing something 100 newtons worth of force, can I in the real world exert 100 newtons worth of force really on that object? No, because friction's going to eat up some of my 100. Vertically, what always gets involved, anything that's moving vertically? Gravity. And that force is called the object's weight. If I have 100 newtons of human pushing force, and I try to do that with a book that's like 10 newtons, my 100 is no longer 100. My 100 becomes 90 because the book's pushing back at me. If I have 100 newtons of pushing force and I want to grab this chair that's probably like 50 newtons, you know, I could do it, but I don't feel like lifting that over my head right now. But would my 100 newtons cause 100 newtons worth of stuff to happen? No, it would actually be more like 50. My desk is probably a couple hundred newtons. So if I have 100 newtons of pushing force, would I be wise to try to hoist this over my head? No, because what's going to happen? If this is more than what I'm even capable of, it's not going up. I'm going down. Like that is not going to work out for me. Okay? Anything horizontal, you're going to have to get friction involved. Anything vertical, you're going to have to get the weight involved. Since the net is always more or less, since the net is less, what are you going to have to do if you're figuring out a net force? Subtract is correct. Maybe you subtract friction if you're going this way. Maybe you subtract the weight if you're going that way. If you're going this way, do you care about friction? No. And if you're going this way, do you care about the weight? No. Just make your choice. If we want to figure out an applied force, we would have to add, because that is going to be the one that's more. You'd have to add friction on, or add the weight on. We're going to use the net force. Anytime we're doing F equals ma, we're going to use the net force, the one that's less, not usually the one that's given to you. So if I start talking about I'm a human, I have 100 newtons worth of force in me, you would or would not use my 100 in this? You would not. You'd have to first figure out, am I pushing this way? In which case you'd take my 100 and subtract the friction. Or if I'm trying to lift stuff over my head, you'd have to take my 100 and subtract the weight. So let's do a couple problems based on that idea. So I have this 2 kilogram object. I'm going to try to do 100 newtons of lifting force. And I want to know what acceleration that causes. What equation would you initially lean toward from your experiences if you're trying to find the acceleration? F equals ma. Do we know the m?
Yes.
Yes, that is 2. We don't know the a. Don't get all super excited today and go, oh, 100 newtons of force, I'll just put the 100 in here and solve this, because you will be wrong. If we have 100 newtons trying to lift something, that is an applied force. We need to involve in the vertical direction, we need to involve the weight. How can we figure out what the weight of this is?
Multiply the 2 by 9.8.
We multiply by 9.8. You could either just go that from memory. On the quiz it said if you want to get the weight, multiply 9.8. Or you could work through this equation with the 2 times the 9.8. This is a mass. This is an applied force. we could figure out a weight of 19.6 newtons. Which force do we want to use in the equation again?
The net.
Net. So how can I get the net force figured out for this?
Subtract the minus
Subtract 2
the 100.
100.
19.
and 19.6. 80.4 lives there. If I'm trying to lift a roughly 20 Newton object, that means 20 Newtons of my force is wasted. Because if this weighed 20 Newtons, right now, how much force do I have to do on it to keep it in equilibrium? 20 Newtons. Because if I did less than 20, it would fall. The only way it's going to ever accelerate is if I do more than 20. So if I decide to increase my life from 20 to 100, that's not 100 newtons that put this object into motion. It's actually ballpark 8. Like the first 20 was wasted by me just keeping the book from falling to the floor. Solve that out, we get 40.2 meters per second squared. Something about that.
How do you figure out if you're going to use net or applied?
Every time you'll use the net force.
Okay.
Up till now, it didn't matter. What they did every time you were pushing is they just acted like friction didn't exist. Okay, there was one question, one time, that they threw in a friction force of 5, if you remember that. And we had to subtract it. That happened once. That's like what we're doing today, every time. 10 Newton object. I try to lift it with 50 Newtons worth of force. I'm trying to figure out what the acceleration would be because of my 50 Newtons of lifting force. So the equation I'm trying to get to is F equals ma. What is the net force? 40. I'm trying to lift with 50 Newtons of force, but I'm getting pushed back by 10. So I have to subtract those to get a 40. I want the acceleration, I need the mass. How can I get the mass out of this? Divide what by 9? The weight. Which number was the weight?
10.
The 10. The 10 was the weight of the object. We could figure out the mass of that object if we take 10 and divide by 9.8. I don't know, 1 point something really low. Somebody punch it for me. 1.02. So 1.02 could live there. And then algebra could get you an answer by doing, dividing. Okay, so somebody get that. It's probably 39.2 unit on acceleration. Meters per second squared. Something about that. This one I have 100 kilograms. I'm going 20 meters per second up. So this would be an example of acceleration. This is a mass. That sort of naturally leads our momentum toward just using the equation. F equals ma by taking 100 times 20 makes 2,000 newtons. What type of force would that be? Disagree? Why do we know it's a net force? F equals ma means net force. Net force means F equals ma time. Those guys are just, they're length at the hip. So we did the equation. That means we're doing a net force. I'm asking you for the applied force. The applied force is bigger. So I need to take 2,000 and add it to what? If I'm going up, down,
The weight.
the weight is involved. What is the weight? Do we know the weight? Not yet, not really. How can we know the weight? 100 times 9.8 is 980. So my grand total is 2,980 newtons. Because with a mass of 100, that's a weight of 980, the first 980 of my pushing is wasted essentially. Like the object is pushing back 980. It takes me 980 of pushing just to even that out. If we're trying to get this acceleration going, we need another 2,000 newtons on top of the 980 it took to just hold the thing where it was. That's the kind of stuff you're doing in the homework. Some of the problems are going to be friction when they go side to side. Some of the problems are going to be weight. More of them are going to be weight questions when they lift stuff. If you're using F equals ma, you're using the net force, the one that's always less. The applied force is always more. Depending on how they structure the question, sometimes you're going to subtract, sometimes you're going to add. I'd say if you're looking for a quick cheat, if you're ready to do F equals ma right away, it's later on you're going to add. If you're having to do F equals some work to get to the F equals ma, then you're probably first looking to subtract before you do something. Question there. Practice test, do the vocab. That'll get you like tips on what the quiz is about. You may have a stray question or two I need to address. I think we've covered most of that, but I think there's one stray question. Let me cover the stray question now. This comes up in the chapter review. In the chapter review, what they have is somebody who's like rising, I think, in a hot air balloon. They have some sort of object that's rising. And as they're rising, they end up dropping something. So most people probably think, if I'm rising in a hot air balloon, and I drop this, that it will immediately fall. And that is incorrect. Does anybody have a thought on what in reality is happening if you're rising in a hot air balloon and you release a thing? What actually happens? It's a question of point of view. So from my point of view, if I'm the person in the hot air balloon who's rising, the moment I drop that, it seems like it instantly falls. But that's only from my selfish point of view because I'm continuing to rise. Okay? If Abby's watching me and we're coming up like this and I drop it, from my point of view, it seems like it fell instantly. She will have a different point of view that is real. A thought?
Is there rest for that?
It will, but even before that. Rest is going to happen, but not instantly. Anybody?
Goes up for half a second.
It's going to rise with me for a little bit. Not as fast, because now it's on its own. The balloon is like pulling me up, and that force is constant. So I'm going up, 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 up. Whenever I drop my object, there's no longer any sort of upward force acting on that, but it has some speed already built up. It's going to rise for a little bit, then it's going to hesitate, then it's going to fall. Same thing similarly happens to you if you're driving somewhere and you launch something out your window. It doesn't end up like back where you threw it. It ends up much farther. Like if I'm driving in a car 60 miles an hour and I see Abby and I'm like, here you go, Abby. It will not go to Abby. It'll end up going to like Raina. To me, it'll feel like it's behind me because by the time it gets to Raina, I'm probably up here to Olivia. Like I throw it, that object's gonna keep going with me to a degree, but I've still got my foot on the gas applying the force. I'm going to be farther ahead than that object was, but it's going to be there. You'll see quarterbacks do that in football games. The guy's running and he's like, I'll throw it to Daisy. Well, there was like a speed there when that ball was released. It's not going to Daisy, it's going to Alyssa. Like if I'm on the run and I'm trying to throw the ball to Cole, I better try to like aim it to Avery, and then it'll like drift with me and end up in Cole. Like that's what's going on with this object. I think that's the last question on there. If you're a rising person and you release an object, what happens? What was it that happened?
It
Rises for a little bit,
And then it's at rest.
comes to rest,
And then it falls.
and then it's going to fall. Homework. We're not going to turn in the old homework because we're running out of time. The new homework's going to go 19 to 27. That is for Wednesday. For Thursday, we will do the chapter review that's in the book. There's an applying problem number 4. That's probably what it is. Probably a hot air balloon or a helicopter or something rising. The review sheet I just gave you isn't due till Friday. And then we'd start off the new grade period day 1, boom, test. Right out of the gate. So that's what's coming up. The 11 to 18, keep that. We'll talk about the 11 to 18 tomorrow. But that was an easier homework, the 11 to 18. This homework's going to be a little more involved than that.